In Millikan's oil drop experiment, a drop of mass 3.2 multiplied by 10 to the power minus 14 kilogram is held stationary by an electric field, and the value is given to multiplied by 10 to the power 5 and c, and n upon c, the number of elementary charges on the drop is. Okay, so if you remember in Millikan oil drop experiment, what happens is that when drop is falling like this, that experimental setup that we have covered in the video, if you provide a particular electric field in that case, and both of the the gravitation force and the electric field and the force applied by the electric field is equal, then the drop will be stationary. So for that, we need to first calculate all those things, and then we can identify what will be the number of charges on that particular drop. All right, so we can start with this concept where you have the gravitation force, which is mg, mass into the g value, which is the acceleration that is being applied by the force of the gravity, and then second one is the electric field, which is QE. So now, since it's stationary in position, so that means both of these forces, they are equal, right? So that means mg is equals to QE. All right. So now we can basically change this Q, and we know that okay, Q is also, we can write NE, number of electrons, and then which is the electric field right over here. Further, if you find out the value of N from this one, N turn out to be mg upon E and capital E. This is the formula. This is the formula that we need to apply, and let's see what are the values that are given to us. So as you can see over here, mass is already given, right, which is 3.2 into 10 to the power 14. Next is you also have given the electric field, which is capital E, 2 into 10 to the power 15 and slash C. You've also given you already know that the value of G, which is equal to 9.8 m upon s square, and the charge E is already known, and for that you need to remember these values at least, right? So this is the standard value that is already known. So if you fit all these values in this particular equation, and I wanted to solve that equation, and you will find out the value is going to be very close to the value 10. So sometimes you will get the answers which are not exactly the value that is given, so you need to find out the closest one. In this case, the 10 is the closest one, so answer is A, right? All other options, obviously, they are just numbered values, they are incorrect. So this is how you can solve these kind of MCQs, and they are really, really important. All right, coming to the next question, which is Rutherford's alpha scattering experiment proved that, I hope you remember that experiment, option A, atoms are indivisible. All right. Next is nucleus is negatively charged. Okay, I think, okay, we'll discuss, after I tell you all the options. C, atom has a small, dense, positively charged core. D, electrons are embedded in a positive sphere. Okay, so I hope you're able to pick up the correct option. If you're not, then please read this question carefully and then try to answer and try to identify the correct option. Okay? Or you can pause the video also. All right, I'm going to give you the answer directly. In this case, option C is the correct one. And now let's discuss why other options they are incorrect. The first one is atoms are indivisible. You cannot divide atom. I think that was the postulate given by Dalton, right? The conclusion from Rutherford experiment was not that. Whatever conclusion were made, one of the point in the Rutherford experiment was most of the alpha particles, because he was experimenting with alpha particles, they pass directly, they pass directly straight through the atom. So that means most of the atom is basically an empty space, isn't it? Empty space. That means there are other particles that are present. Next is some alpha particles, they deflected a small angle. So they move like this, and they have a slight angle. Other one, they bounced even, backwards directly. That clarifies that there is something which is very, very dense in the center, very, very strong in the center, and that was the nucleus. And now you can see that, okay, you can have multiple particles inside the nucleus as well. At that time, it was not proved, but it was proved that, okay, you have a very, very strong core. So in the second option, nucleus is negatively charged. So that's not true. Nucleus is already known to have positive charge. Okay, very easy. See, atom has a small, dense, positively charged core. Yes, positively charged core, which is our nucleus, right? Nucleus, and then electrons are embedded in a positively charged sphere, which is incorrect because they are revolving around the nucleus. And that is why all other options, they are incorrect, and the correct option is this one. All right, now let's move on to the next one. All right, moving to the next question, which is the deflection of cathode ray in an electric field decreases when? Okay, option A, voltage increases. Option B, magnetic field increases. Option C, mass of the particle increases. Option D, radius increases. All right. So take your time. You can pause the video and think of the correct option. And I'll tell you that which one is correct, and then we'll discuss. All right, you can pause the video. The answer for this question is option number C, which is mass of the particle increases. Now, for that, I'm going to give you a very, 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 very short and targeted point for remembering this. Any question like this comes, remember this: deflection. Whenever there is deflection of the electron, because in cathode ray you have electrons, is directly proportional to electric field. Okay, that deflection is directly proportional to electric field and inversely proportional to mass. Just remember that. That's going to save you a lot of your time and also help you to answer these kind of questions, right? So in this case, you can see, deflection is inversely proportional to mass. So the deflection decreases when, mass is going to increase. Simple. So that is why your option number C is correct. Let's identify why other options, they are not correct. Coming on to the first one, A, voltage increases. Increasing, voltage increases the velocity. So now you need to understand that, okay, whenever you increase voltage, that is directly proportional to the velocity. So it's going to speed up the electron. So the cathode ray, they are going to move faster, higher speed, less time in the field, less deflection. So it's going to have impact on deflection. It's going to have less deflection, not more. So you can say it's directly proportional in one way, right? But it's only true if the voltage referred to accelerated voltage. So that we need to remember, right? That is why obviously it's not going to increase, right? So this option is incorrect. Okay, coming on to the next option, which is B, magnetic field increases. Now, since this question is only focused on electric field, so magnetic field is basically irrelevant over here. So we can exclude this option. Then final one, radius decreases. Okay, radius is a result. It's not a cause of deflection. So I don't think it's also relevant. You might have more complicated options than that, but you should remember these kind of concepts very, very critically, so that if anything comes which is closer to this, you should be able to identify these kind of answers very, very quickly. All right, let's move on to the next one. All right, moving to the next one, which is Millikan's experiment confirms which fundamental law? All right, option A, conservation of energy. Option B, quantization of charge. Option C, conservation of momentum. Option D, wave-particle duality. Take your time. You can pause the video, and then I'll give you the correct answer. All right, okay, I hope you have selected the option that you think will be correct. And in this case, the correct option is B. B is the correct option. If you remember, we talked about this before also. Millikan did wonderful experiment. This is one of the important experiments in the history of science. So in that experiment, what he did was whatever oil drop he was using, he was able to make the oil drop stationary, and he was able to identify this particular equation, which is equal to Q equals to NE, right? So he was able to identify that, whenever you have those droplets increased in number, the charge will increase at integral multiple. For example, the n value will have 1, 2, 3, 4 of the fundamental value of E, which is 1.6 10 to the power. So that is the basic charge that will always remain like that, and you will get multiple value just adding to it, like 1 multiplied by this, 2 multiplied by this, 3 multiplied by this, and that explains that everything is, the charge is present, which is quantized in a discrete quantity. It's not continuous, it's quantized. So that is why this option is, correct. Why other options are not correct? The conservation of energy, not directly tested, forces were balanced, but, not energy transformations in that experiment. And C, no momentum measured in that particular setup. So he was not focused on momentum. Wave particle duality was later confirmed by the photoelectric effect. So this option is also incorrect. All right, moving to the next one. When cathode rays are subjected to mutually perpendicular electric and magnetic fields, they pass through the field without deflection. Without deflection if option number A, which is E is equal to B, electric field is equal to magnetic field. Option number B, V is equal to E upon B. Option number C, V is equal to B upon E. Option number D, electric field is 0, E is equal to 0. Okay, take your time. Select the best option that you think based on the knowledge that we had previously. All right, I'm going to give you the answer. Answer in this case is B. All right, I'm going to give you the answer. Answer in this case is B. B is the correct option. Now let's understand how B is the correct option. So if you remember that two forces were acting on those oil droplets. One is electric force, right? Electric force, which is, I can write like this, Fe, which is E upon E multiplied by E, which is electric field. Next one is the next one is the magnetic force, which is Fm, or Fb we can write. Fb, which is equal to EVB. Correct? So now the net force is 0 because that is why it becomes stationary. So that means Fe is equal to Fb, which further means EE is equal to EVB. And from this, if we cancel out the electron, then we have V is equal to E upon B. And from this equation, you can clearly point out that this is the correct option. Not this one, obviously, it's reversed. Not this one, and not this one also, right? So your correct option is B in this case. All right, coming to the next question, which is this. In Millikan's oil drop experiment, another Millikan experiment. Okay, hopefully, after completing all those questions, you will be able to completely understand what Millikan did. That is the objective. All right, in Millikan's oil drop experiment, a droplet remains suspended when? Again, coming to that droplet. It remains suspended when? A, electric force is greater than its weight. Electric force is less than its weight. Electric force equals its weight. The drop is uncharged. Interesting, right? Okay, I'll give you, some time and just please select the correct option. Then I'll give you the answer. All right, I hope you have selected. It's not that difficult one. The option number C is correct in this case, which is electric force equals its weight. Because then this is going to remain suspended in air. It's not going to move. And because of this, it's a wonderful experiment, right? You can stop the oil droplets by applying a particular balanced electric force. So in this one, what happened is one force that is acting on this is the mg. Another force that is acting is Fe, which is QE. This is, it's going to suspend when your Fe is equal to Fg. So your electric force is basically equals to its weight. This is just the weight of that particular droplet. Once it's equal, then it's not going to fall down, right? So this is how you can answer this. And in this case, obviously, other options are mutually exclusive. So you can exclude other options very, very easily. All right, next question is the major limitation of Rutherford's atomic model was. What was the major limitation? Option A, it ignored electrons. Option B, it did not explain positive charge. Option C, it could not explain atomic stability. Option D, it did not describe the nucleus. Take your time, select the correct option. You can pause the video. All right, the correct option for this is option C. I hope you have selected the correct one. It could not explain atomic stability. He was not able to explain why this particular system is stable, as per his model, which clearly mentioned that atom has a dense charged nucleus, right? A dense charged nucleus, and electrons, they revolve around the nucleus like this. All right, okay. So now what happens is, a charged particle in a circular motion should emit radiation. So that is something which was already, been understood by classical electromagnetic theory, that, okay, you need to have those radiation coming out. And because of this, what will happen, that electron should actually slowly should enter inside this particular nucleus. It should fall into this, this electron should fall inside this nucleus. So that means it should be unstable. At that time, this was the concept, and that is why he was not able to explain this, that why this particular atom is stable. So it could not explain atomic stability. It ignored electron, so that is incorrect, because electrons were key part of that particular model, right? B, it did not explain positive charge. No, because it mentioned that there is dense positively charged nucleus present in the center. Last one, it did not describe the nucleus. Well, I think I've added very easy points in here, but I hope the concept is clear, that what was the major limitation of Rutherford's atomic model. Sometimes you are able to understand now, but you will forget. But hopefully you should not be able to forget this particular model. Just remember this. This was the limitation. This was the limitation of Rutherford's model, that why this electron, negatively charged electron, is not directly losing energy in the form of radiation and just falling inside eventually inside the nucleus. All right, okay. Let's move on to the next one. Okay, moving to the next, easy one. Which key observation led Millikan to conclude that electric charge is quantized? Remember, electric charge is quantized. This equation, please remember this. Very, very important question. This is very, very important equation. I don't know why I'm not able to create a very good box around these equations. Anyways, so this is mentioned by Millikan, where n is 1, 2, 3, 4, like that, integral multiple. So in this one, it's very, very easy to understand that charges on all drops were integral multiple of smallest values. Option C is correct. Hopefully you were able to identify this. Others are not correct. And this charges on the drops were continuous. Obviously that's not the case. Charges varied randomly. That was also not the case. They were integral multiple of the smallest value. All drops carried the same charge, right? So that is also not the same. Okay, all right. Let's move on to the next one. All right, moving to the next MCQ. Arrange the following in chronological order of discovery. You need to see what are the chronological order of these discoveries. 1, X-rays. 2nd, radioactivity. Then electron. E upon M ratio. Charge upon mass ratio. Charge quantization. So that means you need to know or remember their the year, the discovery, when it was made, and we'll also discuss that, but hopefully you'll remember that. Option A, 1, 2, 3, 4, simple, just following the simple chronological order. B, 2nd, and then you have 1st, 3rd, and 4th. So is there any possibility of 2nd is being discovered right over before the first one? C, 1, 3, 2, and then 2 is going after 3, so that is another one. And then 2, 3, 1, 4. 1 is going right after this. All right, I'll just remove these lines, and I want you to select the correct one. Hopefully you remember their date. Sometimes question also comes like this in one go. Various other discoveries. People, examiners, they will ask. So you should be able to remember when that particular event happened in that particular time frame. Then you should be able to say the correct chronological order. So in this case, I hope you have selected the correct option. I'll give you some time. You can pause the video also. All right, so the correct option in this case is A. This one, like this. A, not this one, right? A, 1, 2, 3, 4. Now let's see, because the X-rays, if you remember, Wilhelm Röntgen, we understood that 1895 around, he discovered accidentally, discovered those rays, X-rays. So that was in 1895. Next is radioactivity is in around 1896. Henry Becquerel, if you remember, Henry Becquerel. Here I'll write down Willem Röntgen. I hope I'm saying the name correct. Röntgen, and then electron E upon M ratio, which is J.J. Thomson, which is 1897, right? And then last one is Millikan. Millikan is usually, 1909 to 1911, because it took time for him to actually set up this experimentation and all. Even if we take any value, but it's in 1909. So that's the chronological order where Millikan did the experiment where famous oil drop experiment, made him really famous, which is Q is equal to NE. Wonderful equation. Right? This is really good. All right, so that was Millikan did that experiment, and this is the correct chronological order that we have. All right, let's move to the next one. Okay, I'm not going to spend too much time on creating MCQs on these remember kind of concepts, so I'll just explain them quickly. Röntgen 1895 X-rays, and then key reference was EM radiation, high penetration, and all of those rays. Becquerel, which is radioactivity, spontaneous emission, 1896. Then Thomson, 1897, electron, basically E upon M ratio. Rutherford, 1909, nucleus, and then Millikan, 1909 and 1911. That is the charge. And these are the main fundamental discoveries when it comes to structure of atom. Now, quantization was the key concept of Millikan's Rutherford scattering experiment, where he was just bombarding everything with alpha particles, and then he saw that okay, there was some little deviation, there was bouncing back. Most of them just passed the atom, because it was most of the atom is empty space, right? And then you have E upon M ratio calculation, then radioactivity. All those are really, really important. Question can come from any side. So you should be able to understand, the conceptual understanding of every experiment should be really good if you want to clear any exam. And then the application of that particular concept or formula on the data that is being provided is another aspect. And if you are strong in that, believe me, no question is going to stop you from getting very good score in your exams, in your competitive exams, and you will do great. But you need to understand that every concept should be understood in a very, very detailed way. Every MCQ or any kind of conceptual question should be, you should be able to, train yourself in application related questions, in numerical questions. Then you will, when you do numerical questions, what happens is your theoretical concept is also getting refined. All right, so I think we're going to stop over here, and I hope you were able to understand the topic more effectively this time.